Why is artificial gravity hard to add to Starship? Imagine floating in space, weightless and free, but what if you could have gravity just like on Earth? That's the idea behind artificial gravity, but making it happen on a spacecraft like Starship is a real challenge. The main issue is size. To create gravity through spinning, the spacecraft needs a large, rotating section. If it's too small, the spin has to be very fast to simulate Earth's gravity. But spinning fast can make astronauts feel dizzy, nauseous, or disoriented because of disturbances in their inner ear. To avoid this, engineers prefer a larger radius where the spin is slower, but that means building a much bigger spacecraft. Starship is designed to be compact and lightweight, which makes adding a large rotating section very difficult. It would requiring a lot more space, which increases the size and weight of the ship significantly. This means more fuel, more materials, and higher costs. For example, a rotating habitat with a radius of about 100 meters would be needed to produce Earth-like gravity at a comfortable rotation speed. That's for bigger than Starship's current design, which is about 30 meters in diameter. Adding a rotating part also complicates engineering. The structure must withstand stresses from spinning, and the ship's systems like power, life support, and docking need to work smoothly while spinning. Managing the attitude and orbit control of a spinning spacecraft is tricky, and docking with other ships becomes more complex. Another big hurdle is mass. Artificial gravity systems requiring extra equipment like the habitat and support structures. This adds weight, which reduces the payload capacity for cargo and crew. For missions to Mars or deep space, where every kilogram counts, this trade-off is a major concern. Operational challenges also come into play. Starting and maintaining a stable spin without disturbing the ship's orbit is difficult. Docking with a spinning spacecraft requires precise coordination, which adds to the complexity. Finally, current space missions don't see the need for artificial gravity yet. Most missions are short, and astronauts can use exercise routines to counteract microgravity effects. Building and testing artificial gravity systems is expensive and complicated, and we lack long-term human data to prove it's safe and effective. In the future, as space agencies look toward longer missions and even space stations with artificial gravity, these challenges will need to be addressed. For now, astronauts relying on other methods to stay healthy in space, and the idea of spinning spacecraft remains a tough engineering puzzle.